Good afternoon. Today we'll start a lecture series of the assimilation of satellite data in numerical weather prediction models, and we'll see how satellite data are actually useful for the weather predictions. So I will start from the basics of the numerical weather prediction. Then what are the different observations used for the weather models, and then we'll see how these data is actually assimilated into the numerical weather prediction model. So what are the different methods of assimilations, and then we'll also talk something about challenges in the predictions of the extreme weather events, and then observational network for the improved weather forecast. That is, what kind of observation network we can propose to improve the weather prediction. So numerical weather prediction actually is an initial value problem, which is actually given by the Jerkins in 1904, that weather can be predicted knowing the initial condition of the atmosphere. So when we talk about the initial conditions, so what kind of the variables what are required for the numerical weather prediction models are like temperature, winds, moisture, pressure, and all the different level in the atmosphere. So what we call is a volume. So we have to define the atmosphere as well as the surface conditions like land surface temperature or sea surface temperature. So these are the variable. If we know these variable at every grid points and at every level in the atmosphere, so we can integrate the model in the future to predict the weather. So when we see in the nutshell, what is the a numerical weather prediction model, it actually contains the equations which are nothing but all the conservation's law of mass, momentum, and the energy. Then we have numerical procedures to solve these equations, because these equations are partial differential equations where the analytical solution is not possible. So we have to go for the numerical methods. And then we have the physical processes in the models like the cloud formations or the boundary layer parameterizations. Then we have initial conditions of the model which is used to run the numerical model. So in nutshell we have four components, that is equations, then the methods to solve these equations, and then the approximate of the physical processes, and then initial conditions. So this is the in nutshell what is a numerical weather prediction model contain. So when we say the governing equations, so these are the different type of equations which are used in the numerical weather prediction model. So we have momentum, that is rate of change of momentum is actually equal to the applied forces. So that is, we have different forces here. One of the forces is the pressure gradient force. Similarly, this is the frictional force, and this is the coriolis force. So this is the direction, east-west direction, that is U. U is the zonal velocity, that is the east-west. And then V is the north-south, that is meridional component of the momentum equation. And this is the vertical component of the equation. So we have this is a forces, that is the hydrostatic force, that is the rate of change of pressure with height. And this is the gravity, and similarly in this it is the frictional force, and then pressure gradient force, and this is the coriolis force. Similarly we have the equation of continuity, which is called as a mass or conservation of mass. So rate of change of density is given by the advection plus the local advection and then vertical lifting of the air. Similarly we have the heat equations, which is called thermodynamic equation or thermodynamic first law of thermodynamics, where rate of change of temperature is given by the heat advection and then convection. Similarly we have moisture, where we have rate of change of moisture is given again by the advective term and then your evaporation and then precipitation. Similarly the gas, it's a gas equation where your pressure is given by RT, that is your, these are the equations when we talk about a numerical weather prediction model. So these equations are there in a model which we are trying to solve in the future. That is, if we know at a particular time what is the velocity or what is the temperature or what is the moisture, so what will be the value at a certain time after, let's say it is 6-hour forecast or 20-hour forecast, it depends. So we can solve these equations. The problem with these equations is these are all nonlinear equations. These are all partial differential and nonlinear equation where their exact solution or analytical solution is not possible. So we have to go for the numerical solution. So numerical solution of the equation is generally what we do is we do the finite difference method or spectral transformation. So in finite difference method is that derivative can be actually written in like a Taylor series. That is f of x plus del x is f of x plus rate of change of f with x, and you can actually expand this series up to higher order term. Similarly f at x minus delta x, and you can calculate now this derivative df by dx based upon these differences of the forward and backward difference. So this is called a central difference scheme. So we can approximate this derivative with the finite difference, and we are neglecting here the higher order term. So that's where when we see the numerical weather prediction model, so numerical weather prediction model, or you say the weather forecast, is never accurate. So it will always have some kind of error because of we are actually approximating all these equations using these mathematical terms and then neglecting higher order term. So it will always have some error. So this is one example. Actually, if you have equations of rate of change of moisture, where Q is your specific humidity, that how the specific humidity can be predicted or forecasted. So this is a simple term of the moisture advections, that is rate of change of moisture in a given box. Let's say we have a box here and we are trying to find out what will be the moisture after a certain time. We know the initial moisture, what is the moisture at present inside this box, and what will be the moisture, let's say, after 6 hours. So what we are trying to do is we are trying to solve these equations, which is nothing but this is advection here, that is zonal wind, and then multiply by the gradient of the moisture in x direction. So that is what is the moisture at this point and what is the moisture at this point, and similarly in y direction also you can solve what is the moisture in this boundary and then at this boundary. So you can actually take a difference, that is dq by dx. So this is nothing but moisture, this minus this, and multiply by the wind, that is u component, which is actually responsible for the advection of moisture from this surface to this surface. So we can actually solve these equations like this. So we are just taking one term, and just similarly we can do for this y also and z also. So we are trying to see the first term, how actually we can solve it numerically, because this is a partial derivative which is actually cannot be solved analytically. So we are trying to solve this using a finite difference method, where q t plus 1, that is moisture at t plus 1, that is a time after this initial condition, or it's after 1 hour or 2 hours, and minus qt. T mean it's now present condition, and then you take a difference, divide by difference, that is time difference, t minus 1 minus t plus 1 minus t. So it is 1 hour, let's say, and then is it given by, this is the u, this is the mean wind in this box, that is what is the wind in this box, and then what is the moisture in this direction, and then minus what is the moisture at this boundary. So you take the difference and divide by the difference in the distance, that is distance between this boundary and this boundary. This is actually 2 del x. So you multiply this and you rearrange this term. So what we are doing is a q forecast. So q forecast is nothing but q t plus 1, that is after a certain time is equal to q now. Q now is qt. So we are taking to this side, it will become plus minus u del t by 2x. So and QE is east, actually I'm saying this is east surface and this is west side. So Q east minus Q west. So what is the moisture on this boundary and what is the moisture on this boundary? So we are taking a difference and then multiplying by the winds. What is the wind here? Similarly, we can expand this equation all this y direction also and z direction also. And this E minus P is actually what is the evaporation and what is the precipitation in this box. You take the difference. So you can solve it to calculate the moisture at a time after the initial condition. So that's actually the model actually works in this way. Now this is a simple Q forecast equation and very simple equation. We have neglected all this term here. So to make it very simple. So like that we can actually forecast temperature as well as other parameter in a numerical weather prediction model. So when we say the main challenge in numerical weather prediction model, so we have one is the data sparsity. We need a lot of observations to initialize our model, like observation like temperature, moisture, winds, all those meteorological parameter, and then poor understanding of the physical processes, because models need all those processes like cloud formations, how cloud is forming. So we should know all these details. So that is also very limited as of now because of the lack of the observations. Then limitation of the data assimilation techniques. So data assimilation also, when we'll see in later slides, so data assimilation also actually we cannot use as of now all the available observation because of the limitation of the data assimilation, because most of these data assimilation algorithm works for the linear case. So we have a lot of observation which are non-linear related with the model variable. So that also as of now we cannot assimilate these observation. So in nutshell, we need a lot of observations to actually improve the weather prediction, also as well as to improve the model formulation. So in nutshell, observations play a very important role in order to have a better forecast. So we have, when we talk about the weather observation to initialize our numerical weather prediction models, we have different kind of observation. What we call it in situ observations, like we are taking from a radio sonde, we are measuring the temperature and moisture profile in the vertical, and then we have AWS kind of systems, that is automatic weather stations, which provide with the surface observation of meteorological parameter like temperature, moisture and winds. Similarly, our ocean, we don't have other, like ocean is sparsely covered, so we have very limited observations available from the ship or buoys. And then we have some aircraft observation. So these all observations are what we call in situ observations, and these are different parameters which are used for the model initialization, that is vertical profile of temperature, moisture, winds. And then we have the synoptic observation like wind at 10 meter, temperature at 2 meter and moisture as 2 meter, and then surface pressure. Similarly, we have other air reports like vertical profile of the from the air report and along the flight path, because most of the commercial aircraft nowadays have the meteorological instruments. So while landing and taking off, they are taking the meteorological observations of this parameter. So if you see the geographical distribution of the observations are actually, this is a synoptic observation which are available at every 3 hourly, and these are simple parameter of temperature, moisture and winds. And then we have airport, where most of these airport observations are also available at every 3 hourly, surface observation. Then we have most important observation is radio sonde. These are the vertical profile of temperature, moisture and winds, which are available at different level. And we have some pilot observations, then ship observation are available, and then these are automatic weather stations. So if you see in nutshell, a lot of data gaps is there in oceanic region, because there is no radio sonde or very limited ships are available. So we have large data gap over the oceanic region, and even over land also the radio sondes are actually very limited. So if you see over Indian, it is about 40 radio sondes which are launching at daily 12 UTC and 0 UTC. So rest of the time we don't have observation over land. Then we have weather observations from the remote sensing platforms, like we have satellite and we have radars, or we have other like instrument like called GPS RO, that is also one of the techniques which provides the weather observations for the NWP system. So when we talk about the satellites provide the radiances. These radiances are actually related with the vertical profile of temperature and moisture. Similarly, we have scatterometer. These provide the winds near the oceanic surface. These are microwave based scatterometer. It is based upon the radar, this backscattering power, and which can be related to the winds. Then we have weather radars, which provide the radial velocity, and then radar, this reflectivity, which is again related with the winds and rainfall. Then we have wind profiler, and then GPS, that is also Zenith delay total observation, which also related with the temperature and moisture. So these are the different observational platforms which are used to initialize the numerical weather prediction models. So when we say the space-based observation for NWP, we have two different techniques. One is called the infrared-based technique, so in which we have the channel frequencies in the infrared region of the spectrum, where we can actually get the temperature and moisture information using these infrared wavelengths. And these are the different instruments which are used to get the temperature and moisture. So we have ISRO satellite as well as other NASA's and ESA satellites. So these are typical example of these instruments. These are called HERS is actually high resolution infrared sounder, and we have AIRS, atmospheric infrared sounder, then ESC, CRIS, SEVRI, GOES, MODIS, and then India, from India we have recently launched INSET 3D. That is launched by ISRO in 2013, that also actually used to provide the vertical profile of temperature and moisture over land as well as our ocean. So the strength of the infrared based measurement, actually they are good spatial and temporal resolution, and also more accurate. But the weakness is once there is a cloud, because infrared wavelength cannot penetrate through the cloud. So once there is a cloud, satellite cannot see below the cloud. So most of the time when there is a cloud, it is blind to the clouds, and observations are not available over the cloudy region. So that is the disadvantage of the infrared based technique. Then we have the microwave based instruments which are used to measure the temperature and moisture profile in the atmosphere. So the strength of this microwave based instrument is actually they can penetrate through the clouds, because their wavelength is longer than the infrared. So they can easily penetrate through the clouds, and they can give the measurement even in the cloudy region. But the weakness is they are poor spatial and temporal resolutions, because the energy in the microwave is much less than the infrared. So the resolution is actually very poor. To make the signal to noise ratio higher, we are actually having this FOV, that field of view should be very high, and then less accurate than the infrared. So noise in the this microwave actually is more than that of infrared. So these are typical instruments which are used to provide the temperature and moisture profiles from the microwave based platform. So this is AMSUA, that is Advanced Microwave Sounding Unit. It provides the temperature as well as the moisture. Then we have the microwave humidity sounder, and then advanced microwave humidity sounder, METOP. These are the different satellites on which these instruments are available. So METOP is actually satellite used by the ESA, and then AMSUA and AMSUB, these are satellite of NASA's. So in this series, we have own ISRO's and CNES, that is CANES of France Space Agency. So we have launched this Saphir on Megatopics. So this is a microwave-based instrument which is at in the low inclined orbit and provide the temperature and moisture information in the tropical region. So these are the different instruments in the microwave frequency which are actually used to provide the temperature and moisture. So another technique is what we call is the GPS RO, that is GPS radio occultation. So in that also we can get the temperature and moisture profiles. The advantage of GPS RO is actually it's provided the temperature and moisture profile with much higher vertical resolutions. So the principle of this GPS RO is we have one is a LEO satellite, that is called low Earth orbiting satellite. Another is a GPS satellite. So once GPS satellite actually send a signal to the LEO, so while signal is traveling in the atmosphere, it get bent because of the difference in the moisture in the atmosphere. So the signal actually will get delayed. So that delay actually related with the temperature and moisture in the atmosphere. So this is the very high accurate measurement and available for the NWP to initialize the numerical weather prediction model. And the disadvantage of this is actually it is very sparse. In horizontal, you will get something like one observation after something 200 to 300 kilometers. But vertically, this observation is very useful. It has a very high vertical resolution, about 200 meters. And these are the different satellites in which this instrument is available to provide this GPS receivers are there. And then you can have the T and Q profile from this measurement. Then we have a parameter winds, which is again a very essential parameter for initializing the numerical weather prediction models. So generally we have two types of the wind observation. One is called the atmospheric motion vectors. So these are actually wind derived by the cloud. So once we know that there is a cloud and at a certain time, at a certain place, so we can see it in a next image after 30 minutes or 10 minutes from a geostationary satellite, and then we can estimate the winds using this cloud movement. So this is called the atmospheric motion vector, and these are available only where there is a cloud. So these are the different satellites which provide this wind component. We have our INSET 3D and then Kalpana, and these are the other satellites from Chinese, and then UMETSAT, and this is from the US, that is GOES. But another type of winds is available from the scatterometer, and these are available only over the oceanic surface. So we have the ocean surface winds from the ASCAT, that is Advanced Scatterometer, and then OSCAT, that is Indian satellite, and this is Chinese satellite. And then similarly we have other instrument called microwave radiometers. So these instruments also used to for the wind estimation over the oceanic surface. So when we say the what satellite actually instrument measures, satellite won't give you the direct parameter like temperature or humidity. The satellite measurement actually provide you the radiances, and then these radiances are related with the moisture or temperature through this equation, that is radiance is a function of temperature as well as moisture. So when we get the radiances from this instrument, so these radiances has to be actually converted back into the temperature and moisture, because your numerical weather prediction model equations actually contain temperature and moisture, not the radiances. So this problem is called the inverse problem, that is knowing the radiances and then getting back what is the temperature which actually emitting these radiances. So that problem is called the radiative transfer, and it is a ill-posed problem. So the temperature and moisture profile is retrieved based upon this equation is then used in the numerical weather prediction model. So now we'll come to the main data assimilation. Now we have seen what kind of observations are available for the numerical weather prediction model, what are the different platforms which provide the different observations. Now the question is how to use these observations into a numerical weather prediction model. So this technique, so data assimilation is a technique where we actually create the model initial condition from the observation and the first guess. So we have a model forecast available at every grid point, whichever domain you are actually interested in, that then we have a observation available at different grid points. This is, let's say, our domain. So we have forecast of temperature, moisture and winds at a particular time available from a model forecast. So this is what we call a first guess. And then we have observations from, let's say, from any instrument or from satellite. So these are observations. These observations are very scattered, and these first guesses are at a regular grid points. So now our aim is to update this first guess using these observations and to make a new initial condition. So that new initial condition then can be used to initialize the numerical weather prediction model to launch a forecast. So the problem of combining these observations, that is first guess and then observations, is called a data assimilations. So data assimilation is a crucial component of any NWP system, because your NWP system is highly actually depend upon the initial conditions. And so data assimilation provide you your NWP system with a better initial condition so that your forecast can be improved. So in nutshell, a data assimilation process is you have observations and their errors. Here also, we should also know that observation also, we should also know how accurate is this observation and how accurate is this background, so that we can optimally combine this. So we have observations and then we have a model forecast or first guess, and we have the errors of this, and we have a data assimilation system. So this data assimilation systems contains the input from this observation and then background and their error, and then we actually do the prepare the initial conditions. So this process is called the data assimilations. So we'll see in detail in next slide how actually it's working. So data assimilation in analogy, if you can see, is let's say you are moving in a straight road, and if you know that even road is actually a very straight and there is no obstacle, if you close your eyes and you try to actually move your car, so you cannot actually close your car this eye for a longer time. So you have to open your eye with a frequent interval to keep your car on a track. So that's what actually a numerical weather prediction model does. When you launch a forecast, you cannot launch a forecast for, let's say, for 2 days, 3 days without updating your model, because otherwise your forecast will diverge from the reality. So you have to update your numerical weather prediction model with the frequent observations. So that's what actually is actually done by the data assimilation. So a numerical weather prediction model is actually updated with the true observation at a frequent interval of time, so that your forecast is actually on the track, your forecast remain in the certain error limit. So this is just like, if you are, this is a time and this is your some variable, whatever variable you take, whether it's a relative humidity or temperature forecast, or you take a rainfall forecast. So you are launching a forecast, and this is with time how it's evolving. So this is the model trajectory, is the green one, which is going in this way, and this is your observation. So if you don't assimilate this observation, your model would have actually gone to this trajectory, which is quite far from the observation. These are the observation of your atmospheric parameter, maybe it's a temperature or wind. So these are observation, let's say, and you are not assimilating anything. So your model after a certain time would have gone very far from the reality. So now if you assimilate these observations at regular interval of time, so your model is coming closer to the observation. Now this is the green trajectory is now after the assimilation. So the assimilation actually in nutshell does, what it does is actually keep your model near to the reality. So these are the different benefits of data assimilations. Not only the initial condition of a numerical weather prediction model, data assimilation is also used for other variety of the applications. Like you can combine different data sets with a different uncertainty and make a good data set. Then filling data poor regions, you have some observation gap in space or time, so you can also fill those gaps. Then you can design the observing network or the observing systems. So what kind of observations are required to improve the weather predictions? That can also be done by the data assimilations. And you can also maintain the consistency. That is, you can make your data very consistent over a period of time, like for the climate change or other application, you can use those kind of data. Then parameter estimation in the model. So you can also use data assimilation to estimate the parameter, like from the radiances you want to estimate what is the temperature or moisture profiles, or what is the wind speed from the scattered signal from a radar. So all those things can be done using the data assimilation. So we have different method of data assimilation. So one is called sequential method, in which we have optimum interpolation and then Kalman filter. And then other methods are called variational method, where we have three-dimensional and then 4-dimensional variation method. And we have hybrid method, where this sequential and variational method are combined. We call it hybrid method. So we'll see one by one actually what is done in the sequential and variational method. So the optimum interpolation, if you see actually how optimum interpolation is working. So let's say you are trying to estimate the temperature where you are sitting, let's say in your room or in your classroom. So let's say we want to estimate what is the temperature inside our room. So let's say we have two information. One is from a thermometer. Let's say a AWS measurement from your campus or somewhere. So we have AWS measurement temperature, and then we have information 2 is 6-hour forecast. So we have two information about a particular place. So we are now want to estimate what is the best, whether this is accurate or this is accurate. We don't know. So what we can do is we can combine these informations and then make a best out of these two. The truth is, let's say truth is T-truth. The truth is actually we don't know. Truth is just a theoretical concept. So we don't have the truth value of the temperature. So only we are having these observations. So let's say now this TO is truth plus some error. And similarly this B we can represent, or we can formulate this background temperature into truth plus some error. So this T-truth, though we don't know, but we can actually make this equation that this observation is equal to truth plus some error. Similarly, this is also a truth plus some error. Now we want to combine these two to make a best temperature. Because we cannot simply say that there are two temperature values. We have to say to public that there will be one temperature forecast, whether it's a 23 degree or 24 degree. So we have to combine these two information to make it a one. So how we can combine is, there is one way is to combine the linearly. So we can take a temperature, final temperature is equal to alpha 1 plus TB plus alpha 2 plus TO. So we can combine them, and we are making some assumption, that is these observations are unbiased, that is there is no systematic error, and similarly they are uncorrelated. So and then they are normally distributed. So these approximation if we make and we combine them, so we'll get that alpha 1 plus alpha 2 is equal to 1. That is the total weight. These are weighting factor. So this weighting factor will be 1 if you assume these criteria. And then if you minimize the variance, so this is our final temperature, and we have the truth. So you take the difference of this and make a square both the side, and then you minimize these equations. That is, you take the derivative of this and keep it equal to 0, and you find the temperature finally. So you will get this equation. That is, final temperature or the accurate temperature is T of B, that is this temperature, plus K, and this is a difference of these two. And this K is called Kalman gain, or it's a weight matrix. So this weight matrix is given by this B plus R and B plus R inverse. So B is nothing but what is the uncertainty in the temperature TB, and this R is what is the uncertainty in the temperature TO. So that is actually nothing but error variances. So if you know what is the error in this temperature and what is the error in this temperature, so we can combine them using this equation to get the best out of these two. So the final temperature will be this, and this is called optimum interpolations. And the final temperature will be having error less than both. This is TO as well as TB. This can be proved using all these equations, because detail is not possible here, but this is the final equation where what we call optimum interpolation. So that is a basic step in the data assimilation, how a data assimilation is working. So we are taking different observations and then combining them based upon their error statistics and getting a best or the optimal value based upon this information. So this is for a one value, that is scalar case, that is you have 1 point available and then you have 2 observations for this particular grid point. So now to generalize it, let's say you have n number of parameters or you have n number of grid point in your model. So to generalize this equation, we can write into this form, that is x of a, that is the final variable. Now this x can be any variable. It may be temperature, wind, or rainfall, and then this is xb, that is another variable or the background or a forecast which is available at every grid point, plus this is a k, Kalman gain, minus y is nothing but observations, and then h of xb, that is difference of these, and this is a weight matrix. So you calculate this weight matrix and then you add this value to this. This is called increments. There is a difference between two observations. So this is actually called in the is a vector form, that is a column vector. So this xa contain all the observations whatever available, that is x1, xn. Similarly y observations, n number of observations, and then this b is a, there it was simple error or error variances, now it become a covariances matrix, that is correlation plus variances, and this simple r is also a error in the observation. So now it's become a very big problem when we actually take a lot of grid points and a lot of observations. So this is a typical dimension of a numerical weather prediction model. So x is the dimension, that is 10 raised to power 8 is total number of variables. Similarly, this x actually is from x, y, z, that is your x direction, y direction, and z direction, because it's a volume. And then variable, this is the number of the variable. So we have generally 4 to 5 variable, that is temperature, moisture, and then 2 component of the wind, and then geopotential heights. So we have typically 5 variable. So if you take your model of 1 degree by 1 degree and a global model, so you will be having 36 point in x direction, 180 point in y direction, and vertical level in z direction. If you take from, let's say, from surface to about 20 kilometer and you divide into a layer of 1 to 2 kilometer, so you will be having roughly 22 to 25 different levels and then variable. So you multiply this, you will get the total dimension. So this is a total dimension of about 10 raised to power 8. But we don't have all the observation available. So we have observation available one order less. So observation are available of the order of 10 raised to power 7. And this is your matrix. So this matrix is actually a very big matrix, because it is actually a square matrix of 10 raised to power 8 into 10 to the power 8. So it is become a very big problem. So what is now this H? So H is, we call it observation operator. What it does is actually, if let's say we have a radiance available from satellite, but we are trying to get a variable temperature from the model. So this is radiance now available from a satellite, and this is the temperature. So what H will do is actually it will interpolate and it will convert this radiance or the temperature into radiance and then compare with the radiance and then calculate the differences. Similarly, this H will also do an interpolation operator. Let's say we have, these are the model grid points and our observation is available somewhere here. So what this H will do is it will take these 4 points of the model and it will calculate the model observation at a observation point from the model grid point and then calculate the differences and then add to the original value to the grid points. So this H actually is called, generally has 2 functions. One is the spatial interpolation, another is the variable transformations. Like you are assimilating the radial velocity or radiances or GPSR or effectivity, then this H is called the variable transformation. This is one simple example. Let's say we'll do one very simple example taking a scalar case, that is these equations. And now what we are trying is we have 2 points. Let's say we are trying to find the temperature over Ahmedabad and let's say Delhi. These are we are taking only 2 points and we have a background, that is a model forecast is also available over this point at a particular time. So over Ahmedabad it is about 20 degrees centigrade and it's Delhi is about 13 degree. And observation is also available, let's say from AWS or from other sources, which is about 24 and 16 degree. So now we want to actually calculate what is the best value, what is the optimal temperature over this location. So what we are assuming is an error in the, this B is actually error in the forecast. So the error in the temperature at Ahmedabad is 2 Kelvin or 2 degrees centigrade, and then Delhi temperature error is 1. So these are the diagonal element, what we call it the variance, and these off diagonal elements are called covariances. So what we are assuming is these observations are not, that is temperature at Ahmedabad and temperature at Delhi is not correlated. So this will become 0. So this is our background error, and similarly error in the observations, that is error in the temperature at Ahmedabad is 1 and at Delhi it's about 0.5. And this again is what we are assuming is these observations are not correlated. So your off diagonal element becomes 0. Now if you see what is the background error matrix is your variances and then variance at Delhi, and this off diagonal element is the correlation between Ahmedabad and Delhi, and then this is again Delhi and Ahmedabad. So these are actually essentially same because it is symmetric matrix. So we are neglecting at this point of time, or we can include if you have all this information. So now our aim is to find out the temperature at Delhi and Ahmedabad knowing these 2 information. One is observation, another is the background. So what we are doing is we are estimating the Kalman gain, as I have shown earlier. What is the Kalman gain is that B plus R matrix and then take the inverse. So this is a B plus R matrix and then inverse. So this is the inverse of this matrix, and then you apply these equations into this. So temperature at Ahmedabad and Delhi is equal to background temperature at Ahmedabad and Delhi plus this Kalman gain. This Kalman gain is K, which is given here. So this is this much, and then this is the Y minus H of X. So Y is observation at Ahmedabad and 16 is the observation at Delhi, and then difference H of XB. Now what we are assuming is that this observation location and then model grid point are at the same location. So H will become a simply identity matrix. So this will be 1. So this is the background value 20 and 13. So you take the difference of these and then propagate these differences based upon this Kalman gain. You will get the final temperature. So this is the simple matrix multiplication and then addition. So the final temperature of Ahmedabad and Delhi you will get is 22.66 and 15.0. The original temperature was this much and this much. So it is in between these, right? So this temperature will be more closer to the observation if observation error is less than the background error, or it will be more closer to the background if the observation error is more than the background. So that's why it is actually called the optimal interpolation. Now these are the different role of this background error matrix. What else it plays actually role is to spread the information in the X or Y directions. So this is also done by the B matrix because of the covariances. That is, if observation of this point is correlated with this another point, so that whatever change you are making here, it will also influence the other points. So that's what we call is the covariances. So this is actually how we can estimate this background error and all this matrix. I will not go into detail of this, but it is actually how to calculate this B matrix. What is the error in your forecast? So essentially what we are doing is we are comparing with a model forecast with the observation to calculate the background error covariances. And this plays a very important role in the data assimilation because the exact value of B is very essential to actually get the proper scaling of the differences and then to get the final analysis. Similarly, then this is the observation matrix. What is the error in your observation? So what is the uncertainty in the observation is called the R matrix or the observation error matrix. So this also represent the error of representativeness and then error of the observation or the instrument, whatever the instrument you are using. So you should know all those information regarding this R. And this generally observation error correlations are often assumed to be 0. That is, we are generally taking a diagonal matrix. Otherwise, while inverting the matrix, it will be very difficult. So generally what we assume is the observation error are uncorrelated in the data assimilation. Then what is the drawback of this OI technique? Generally we can't use the OI technique because of the computational resources. So if you take a typical problem of this, what I had discussed is the degree of freedom is 10 raised to power 8, and you try to calculate this Kalman gain, which is actually you just one example is given. If you take a just simple computer of having a clock speed of 2.5 gigahertz and it's about 10 gigahertz flow per core, and the number of operation what we require for this matrix multiplication is actually n raised to power 3, that is order of cube. So the CPU time required for this particular application will be about 10 hours. It is in years. So you cannot actually use this OI to calculate this kind of analysis problem because it actually requires the matrix inversion, which is a very difficult problem. So we generally avoid this OI technique in the data assimilation because of the computational resources. So in order to avoid this OI problem, we have another problem called variational problem, in which we actually avoid this matrix inversion and we solve the problem iteratively. So in variational problem, what we do is we assume that observation and background error are Gaussian. So this is one Gaussian distribution formula, that is observation error is Gaussian as well as background error are also Gaussian. Now we are trying to find what is the probability of P, that is probability that T will be truth. So the combined probability will be, if you get this joint probability, you multiply this, you will get this. So now this probability will be maximum if this will be minimum, because it's a maximum, this negative of the exponent. So if you increase this or you decrease this, then this will become higher. So our aim here in the variational problem is to minimize a cost function. So this we generally denote as a cost function. So cost function is nothing but a T truth minus TB, that is a background information, and then T truth minus observations, and you minimize this cost function. So you take the gradient of this cost function and put it equal to 0. So you will get the T truth. So in this case, what we are doing is we are avoiding the inversion of the metric, so that our problem can actually solve computationally faster. So this is one typical example of the cost functions, that is a cost functions. So here we know the xb, we also know the background error, and we also know the observation y. Our problem here is to find the x. So we are solving this cost function, and the point where this cost function is minimum, that value of the x we consider it as the most optimum value of the x. So here we can use the iterative solution, we can use the any method like Newton-Raphson method or conjugate gradient method. So the simple Newton-Raphson method, where we are trying to find the solution of this equation using this Newton-Raphson method iteratively. And this is how it will look. This, we are starting from here and we have to reach the bottom, that is the minimum of the cost function. So this is a bell-shaped cost function because it's a quadratic equation. So in variation problem we can solve it quite fast than the OI problem. So similarly, this is a 4D var is also similar to 3D var. Only thing is one more time dimension is there. That is, we can actually use the observation distributed at different timings. So in this, if you are making analysis at 00 UTC, we can use the observation even available at later time. So that is a difference between 4D var and 3D var. There, time dimension is also there. Then we have drawbacks of variational method also. One is this background error covariance in matrix is generally we take is a climatology. That is, if we are making a initial condition for, let's say, this hour, so we are taking this B is a climatology, that is a monthly mean or yearly mean value we are taking. We are not taking the error of the day, that is particular error of the day we have to consider in order to minimize this. Then this problem is now we will take in the Kalman filter. So that is the drawback of variational method is the climatological value of the background error. So other method is the Kalman filter. Is what we do here is we actually propagate this B. That is, B also we can forecast. So what is the error as of now in your background? What will be the error, let's say t plus 1 time also we can forecast or we can calculate. This technique is actually called Kalman filter. What in Kalman filter what we do is we actually calculate the Kalman gain as earlier you showed at a particular time j, and then we make a initial condition. Now we know this error in the initial conditions. So this is the error in the initial condition at a particular time. Now we can propagate this error at a later time, that is background error at a particular later time is given by the this error at a initial time and plus the model. So we can propagate this B, and this propagated B can be used for the later time instead of a climatological background. So we can use this B. So that is the advantage of Kalman filter, is to use the background error for the exact time at which you are making a initial condition. But this Kalman filter is not feasible as of now because of the again computational resources. This propagation of background error matrix actually is not feasible. It requires a lot of computational power, which is not available as of now. So in principle, it is this Kalman filter is the best data assimilation technique, but due to the computational resources and the linear nature, because or no linear, it may not work. So this is not applied as of now. Then the simplified versions of this Kalman filter are available. Like one is called extended Kalman filter, where we are doing some kind of modification or simplification into this to actually use or to make it more computationally faster. So one is this, we are using this first order differential equation, that is tangent linear model is used instead of the full model to propagate this error. So that is what we call as extended Kalman filter. This nowadays people have used it to a certain extent, but still this is also a very computationally expensive technique. Then another technique what we now people are doing is called ensemble Kalman filter. So that is widely used nowadays in data assimilation. So what we do in ensemble Kalman filter is we take the initial condition. We have a one initial condition and we know that it is not perfect. So what we do is we perturb that initial condition and make, let's say, 10 initial condition using some error in the, or using some noise, and then we make a 10 forecast from that particular 10 initial condition, or whatever, how many sample you are taking, you can take even 50 or 100 also, and then we have different forecasts. Definitely they will be, forecast will be different because initial condition is different. Now we have observation here, we assimilate these observation into this different forecast and then make an analysis, and then we make again a forecast. So here what we do is we can actually calculate this background error using this ensemble spread. We take a mean of these and calculate the standard deviation of each of these, and we can approximate this background error for a particular time step. and then this updated background error can be used while making the new analysis. So this is nowadays technique which is widely used, and it is computationally affordable. So this gives a better initial condition of a numerical weather prediction model. Then we have a hybrid data assimilation. What we do in hybrid data assimilation is we combine both. That is your variational as well as sequential method. So what we do is in error propagation, we use ensemble Kalman filter. That is I showed in last slide. While analysis step is done like 3D var or 4D var. That is, we minimize the cost function instead of getting the direct OI kind of thing. So we do the variational plus ensemble Kalman. So that's why they are called hybrid data assimilation. So the hybrid data assimilation actually combines the strength and the of both variational and sequential method. And this is how the solution of these all three techniques actually look. So in variational, if you use variational, then you have a homogeneous spread of this information. While in ensemble Kalman filter, you have flow dependent. That is where your flow is there, whether it's a wind or any kind of flow. So your increment or the differences will be along the flow. Similarly, in hybrid, you have a more elongated and taking the advantage of both. So that is the difference between these. Now, these are the different methods of assimilation. Now, what is the impact of these different satellite data on numerical weather prediction model? So this graph shows actually this is a year in different year, and this is the skill. So you can see that skill of a numerical weather prediction model increases with the time. So this is the time. Now this is about 2014, and this is 1980. So you can see from 1980 to 2014 roughly how much increase is there in the model weather prediction skill at the different southern hemisphere, northern hemisphere, and different forecast length. So in nutshell, the total this contribution of the satellite observation is about 10%. So there is a 10% improvement in the model this weather prediction of this due to only the satellite component. So that is the how many satellites or how much data is available, but the model only could improve the 10% of the data, because most of the data is as of now is not usable because of the certain limit in the data assimilation or non-linearity in the observation. But even a 10% gain in the weather prediction skill is actually obtained purely because of the satellite observation. This is impact on extreme weather event, that is like tropical cyclone or this last slide where impact was actually all the weather condition. It's a normal weather condition or taken all those weather condition. But this next slide shows the only the extreme weather condition like tropical cyclone. So if you can see, the tropical cyclone track error has been drastically reduced from last 1980s to some 10 or 14. So the track error is now actually drastically reduced because of the satellite data. Again, this is about 10 to 15% improvement in the cyclone track forecasting because of the satellite data. But the intensity of the tropical cyclone, this is the intensity trends, how the intensity error actually decrease evolving with the time. So intensity error is almost constant throughout the period. So there is not much improvement in the tropical cyclone intensity predictions. This is again because of most of the observation. Once there is a tropical cyclone, so you have a lot of clouds there. So once there is a lot of clouds, your infrared observation are not usable because it cannot penetrate through the cloud. So you have a lot of data gap. So you don't have any observation to initialize your numerical weather prediction model. So it is not justified actually to accept this improvement in the intensity. So that's why the intensity improvement is very marginal because of the satellite data. So intensity prediction of a satellite, actually the tropical cyclone is still a challenge. Then we have the other events like thunderstorms. Again, the situation is same. When you have a thunderstorm event, because it's a very localized event, and then initialization of numerical weather prediction model in a thunderstorms is again a very difficult problem. So we have very limited skill even in a thunderstorm prediction because of the data gap. Most of the satellite data is again not available once there is a cloud. So microwave is available, but this is also once there is a rain. So microwave also not available because there is a lot of scattering once the rains are. So we have a lot of data gap, and we don't have the crucial observation which are used to initialize the numerical weather prediction model. This is again the application of satellite data to detect the dust event, and then to predict the dust event also. Model can be used to predict the dust event. This is one of the dust event which could be predicted with the model successfully. Now, what is the role? How DA can be used to actually define the observation network? So, DA data assimilation can be used to define the observation network also. That is, what kind of observation we need to improve the weather prediction over a particular region. So, using the data assimilation system, we can actually calculate what kind of observation we actually need to our region to improve the weather prediction. So, as of now, in most of the numerical weather prediction model, satellite data is used about 80% of the total data is from the satellite data or from the space-based component, while 20% of the total data is from the terrestrial component like radio sonde or from the SIP or AWS. And similarly, if you take the observation wise, the mass observations and the wind observation. So mass observation is about 70% of the total data, while the wind observation is only 30%. And wind observations are very essential for tropical region. So we actually need the wind observation or tropical region to actually improve your weather prediction. This is one of the another results where we show that which kind of the observation has maximum impact over the weather prediction over the Indian region. So this again shows the wind observation are very important when we talk about the tropical condition. If you go to mid latitude or the countries like Europe or even the northern USA, where mass observations are very important, that is temperature observations are enough. But when we actually come to tropical regions, we actually we should have the wind observation to improve the weather predictions. And that shows the instrument wise, that is radio sonde is the best instrument to improve the weather prediction. Now, what are the different observation or the future scope where we can improve the weather prediction? So one is the assimilation of the cloud affected, because as I told you, once there is a cloud, most of the observations are not actually used in the data assimilation. Then another is the microwave rain affected radiancies, and then use of the high spatial and temporal resolution observation from the geostationary satellite also very much needed. And then we have current observing network also. Actually wind observation are not available as of now from different level in the atmosphere. So in future we are planning this space-based Doppler radar. It will be launched by the ESA in this 2015 or 16. So that will also help to improve the weather prediction over the tropical regions. Another, the temperature and moisture profiles of adequate vertical resolution is also very much required in the cloudy and rainy condition. So these are some of the things what actually can be think of in near future to improve the weather prediction. That's all from my side.